make corrections for. So the part I want to cover in terms of the whole process of getting 3D reconstruction is the part that once you have several images, you have images of different tails, then you can put them together before you sample it and it reconstructs the 3D images. There's three parts to it. One is to how we use the Oracle Tilt program to merge multiple images to common face origin, scale, and other things. And there are some fitting, how to fit the lattice line and how to use. And I want to spend some time to tell you how we can use all these results to improve our image acquisition and the processing. So Oracle Tilt program in MRC package does a lot of things. Its main function is to move, in the projection image cases, which is the easiest to understand, is to move images that we acquired to a common origins, so that allow us to do an averaging. Because if they are not at the same place, and you may imagine that you're not going to get a crisp image, crisp averaging of your dark pictures there. So to do this, that it needs references, and no matter when you are moving two things together, something has to be the reference. So there are three kinds of references that you can use in the program. The first is the symmetry, so-called special positions. These are like rotation axes. If you have P2 symmetry, P4 symmetry, that's rotation axis. Now, in the Z direction is one of the best places that's to be used as the reference. So that will automatically be used. The second kind of reference that you will use is that after you have merged a few images, then you can use that as your reference. So that the newer images will be put onto the same origin with the others. Now you can imagine if you have a P1 symmetry crystal, that would be the only way that you can do it. So you use the first one as your arbitrary reference, and then merge everything else to it. And the third situation is that once you establish a larger set of data, you have a 3D model, then you can use that as your reference. That's also a very good way of doing it. When Oracle Tilt program is run, you can do several refinements. One is, of course, the face origin. And the other thing that you can use it for is for refining the tilt geometry. And you can also use it for refining beam tilt once you get to higher resolution. Okay. While you are doing this, there are a few things you need to consider. This actually comes from that when we acquire our data and when we assign the axis, we are not, there are certain information we don't know yet. So you may call it a mistake, or is it just a convention decision that you put in, to determine your lattice that you actually need to make adjustment for. So these are really big changes. For example, you need basically what we're doing is try to standardize your AB axis relative to your image. So for instance, we decided that this is going to be our A axis in blue, and this was the B axis. That's in our reference. Now, your image that comes in, it may be that when you acquire the data, this crystal is turned around 180 degrees. And when you assign your axis, you still use your right as your axis and the top as your y-axis. Then when you take that, rotate the actual structure around into this direction, those two axes will actually be rotated 180 degrees. So in this case, all your amplitude interfaces that you define in there needs to be converted into the correct axis. So that's what it needs to deal with. So there are flags inside the program that allow you to do this sort of conversions. And there are other cases as well. I try to describe a few of this here. And the other one that's common is that you put a crystal down there unless you have two-fold or two sub one axis in the plane of the crystal. When you flip it upside down, you don't get the same structure once you start tilting. So you need to consider that as well. So it's possible that you may need to take the axis that you used before need to be flipped upside down in order to have the same structure inside your unit cells. And then the third situation is that you have over-focused images collected accidentally, which is not distinguishable, that especially in the very low contrast to the crystal images. Then you may need to actually invert the sign of your CTF correction. So these are things that you may have to do. Okay, so the merging process, that's also been covered a little bit. So basically, that the idea is that we will start off with images that will most likely to have the same values in the lattice line. So the easiest way to do that is to take untilted images. Now you put your stage into zero tilt, you collect a few of the images, try to merge them together. The assumptions that's been made, as already been pointed out by Bert, is that you assume that within certain range of these stars, that the value can be considered as the same value. So you can take the value you get at for a certain lattice line, that you can take the value that you obtained from each image, just average it and use that as your initial guess. Okay, so that's the first round of merging. When you're done with that, you have information up to your resolution limits that you did your merging. Now, what you would do next, then, is that we have, so far we assume that we have information up to this point, up to this height of the Z start. So when the next time that what I will do is I will take images as higher tilt. This time I probably assign it to the next tilt, that I have a certain amount of overlap. Now, when I tilt it like this, the resolution range within this in my reciprocal space is going to be still lie into this box that we from the beginning we assume that is going to give us the same value. So you can use that value to find out the correct phase origin of the tilted image using this part, and then that origin, once you apply that, you end up with information from the ones that's outside this zone. Of course, when you are doing this, it will be the best idea to do a number of them. So you will usually take not just one tilted image in the merge. Each time when you do this, it's best for you to take a group of them. That way you build up not just one line, but more like a zone of it. And that would look like something like this. Okay. So when you are done with that procedure, now your information, the zone, the volume that you have information in the reciprocal space has expanded, so that it gives you more like a band of information up to that tilt. Then what we'll do then is repeat this process to higher tilt again. Then you go to higher, using higher tilt, there will be a part of that image is overlapping with the region that you already have information. So that allow that to be merged with the others to the same phase origin. So you will end up building up with even larger volume of information. So as we continue with this, then everything will work fine. We'll get higher and more information into our data, into our merged data. Now, one thing very important is that not to start off with very high tilt. This is very obvious from when you look at what we have been trying to do here. We've been using the available information from the last merging to build up to find the origin of the one that has tilt that has data that's outside the range of Z star that we already obtained the information. So if you use something that has very high tilt, the result would be that the zone that you actually can be used for your origin refinement is a very small portion of the whole reciprocal space. As a result, you have a smaller number of refractions that you can use for comparison with your reference. So that's not going to work very well. You're not going to be able to get a very good phase origin, in particularly in this direction, as you can tell. So that's something that you should not be done. Okay, so the next part I want to cover is lattice line fitting, and this is done in a program called Lat9K in MRC. The purpose of this is instead of drawing by hand the lattice line, you will actually use a model that's a reasonable model to fit all your data in the Z star space. So we have all this lattice line in a space. Then if you draw that in the Z direction of one of them, you get here this direction is the Z star, and then you can draw your amplitude and the phases on it. Then try to fit that. The way this works is basically a model. If you ever look at what you need to define in the lattice line fitting program, there are a lot of parameters which I show here. I'm going to try to go through a little bit of what these are and what you should watch out for. Okay, so the first thing is that I'm going to try to think about 2D crystal in a different way. We can think of a 2D crystal as we start off with 3D crystals that has a repeating pattern in the Z directions. So, a very simple kind of structure would be, let's say, it's just a cosine wave in this case as your structure in that direction. To go from a 3D crystal to a 2D crystal, now what you really are doing is apply an envelope function to this continuous function that's keep on going in real space. Once you multiply that with an envelope function that's limited information to be within a certain distance, then you end up with a structure that has information that will have values not equal to 0, only within that range. So in effect, that we are cutting off all the other layers of our crystal and make it into a 2D crystal. Okay. So the reason I want to think about it this way is that in Fourier space, then we can do something really fun. So a sine wave, a cosine wave, then if you Fourier transform that, as already mentioned yesterday, that you will get 0 all over the place except at plus and minus 1 over c. Okay, so c will be the repeating distance here. The envelope function is Fourier transform into a function looks like this. I'll explain it a little more. We know in the real space, we multiply these two together, we end up with our 2D crystal. So in Fourier space, what we can do is, well, what we will end up doing is that we convolute this simple function with this function with just one peak. Then you will end up with what are our continuous functions, like what we see as a lattice line. Okay, so we went from a discrete function in the Fourier space to a continuous function. So what does this one look like? That function turns out to be a sinc function. If you have a square wave, when you Fourier transform that into reciprocal space, you will end up with a sinc function. Now, if we separate it out, you can see that this amplitude has a peak, at 0, or the middle of your box, and then it goes to 0 at 1 times 1 over d, and also at 2 times 1 over d, and also 3 times 1 over d, etc. Every time that it reaches 0, it really is having a phase flip. So you will see that the phase goes 180 degree change whenever it goes to 0. Okay. So there's something called Whittaker-Shannon sampling theorem. It's a very useful theorem for 2D crystallography. What it says is that if your density is limited within the envelope of width d, like what I showed before, that is transformed, maybe reconstructed by values that you found out at discrete points. So you can just do it. If you know the values at 0, plus minus 1 over d, plus minus 2d, 2 over d, etc., then you can actually reconstruct the whole thing and taking those values, convoluted with the appropriate sinc function. I'm going to try to illustrate that point here. So here we have some sinc function that we know certain width, and I end up with a sinc function in a z star equal to 0. At a 0 point, that we know that it has an amplitude of 570 and a phase of 0. This is just an example I came up with. And we also know that at 1 over d and minus 1 over d, we have an amplitude of 950 and certain phases. Now we know this two information, and we can actually plot this out, knowing this using the behavior of the sinc function. If I'm going to try to add these two together, then you will see in the green line, when I add it together, certain things happen. So you notice that at certain points, the value hasn't changed that much. For example, as z equals 0, my amplitude value is still at 570. My phase is still at 0. And at 1 over d and minus 1 over d, my amplitude is maybe only slightly off from the original 950. And its phases and also remain the same. That's because for the z equal to 0, it drops, the amplitude drops to 0 when it get to 1 over d. So what this means is that we can, if you want to describe, a curve, if you don't know its form, then you actually have to know every single point. So if I want to fit that curve, then I have to use many number of parameters to fit that. By using the Whittaker-Shannon sampling theorem, it reduces the number of parameters I need to fit now, because I only need to know the width of my envelope. I only need to know that the values that I have at all this position, 1/d, 2/d, and all those places. So it makes the fitting more feasible. And the other consequences of that is that you haven't observed that the damping of the amplitude means that the contribution from a turn that's away from your originally assigned peak position is reduced. So, for example, you can see that even though we have some values over here on the next one, that the value is the amplitude hasn't changed much over there on the second peak, because for the 1/d turn, because the z star equal to 0 turn has a very small amplitude there. The reason I want to mention this is that there are cases that your fitting is not very good, and if it is not fitting very good, people sometimes think, oh, maybe I just need more data, okay, and they take more data at a higher tilt. Because of this behavior, you're not going to really gain that much, but to give you better fitting at a lower z star value. The example here I have, let's say now I have this much of a tilt, and I have this fitted. If I delete out most of my high tilt data, you see that the behavior over here hasn't changed much. If I flip it between the two, you see there's a very slightly differences in the way it fits, but it's not going to affect your general shape. So in other words, that this approach is not going to help you. So how do we make a general fitting better? That can only be achieved by having the correct envelope function. Now the idea here is can be explained easier. That when you think about it, you have a data points here, and then you want to fit some polynomial function to it. Now people at first, let's say you fit it with a straight line. This is not going to fit very well. There are small number of parameters, but that's not enough to describe the behaviors of the curves. In this case, a second order polynomial is going to give you a much better fit that describes your data. So you should use more, even though it requires more of the parameters, you have to use that many of parameters to describe your function. So same thing happens when we are doing lattice-line fitting. Remember, the envelope function describes the envelope, the width of your envelope determines the width of your sinc function. So in this set of data, if I use my envelope of 260 angstrom, this is a gap junction crystal. So it's it's like it's 2 bilayers. So basically, it's a 2-layer of a protein. You get the 2 sets of transmembrane proteins in there. If you in the practicals that you will see this set of data, the map. It's especially thick. It's much thicker than a normal membrane crystal. And so I have to use 260 angstrom to fit the lattice line. in order to follow the trend of all the data.
How did you pick 260, not 250 or 300 or 400 or 1,000?
Okay, so I'm going to go a little bit. I will try it, and I will try to show you in the next slide, and then we'll come back to that point. Okay, so if I choose 100, then this will be obvious. This is definitely too small an envelope, right? So you can tell that this is not going to fit well. When you have a small envelope, what's going to happen is that you are in your reciprocal space, your think function becomes wider. So overall, the peaks are overall your curves that you obtain will be smoother, right? So this obviously has more movement than what that function will be able to describe. Okay, so it's very obvious 100 is not going to work. Within certain range, you're not going to see a lot of differences. If I change it to 240, 250, maybe 280, I probably won't see that bigger differences. But if I go to 500, then I will start to see the differences again, because if I go to 500, I'm starting to overfit, right? That was originally be something that to have you to think about, because in a polynomial fit, you can keep on adding parameter and parameter. Eventually, you're going to fit every point because you're not doing fitting anymore. Your number of parameter, your number of data, if this becomes equal, it's not a fitting. And you can get every point on your line. But as you can see, that's, it means very little if you try to interpolate it. If I'm going to try to know the value at this point, I'm going to get it totally wrong. So that's why you don't want to go over. Okay. So in the same way, in the lattice line, if you use a too large an envelope function, you're going to see a lot of changes, modulations in your fitting. In the data point of at some point, in order to use a 3D crystallography program to reconstruct your structure, you're going to have to sample. In other words, interpolate the lattice line. So if you use something like that, something that's really big, then you're going to have problems because your interpolation may not fit right onto a point. Does that make sense? Yeah.
One of the arguments people made a while ago is that you should use the imaginary lattice in the z direction to be 2 times the thickness that you think your object is. And the argument for that is that the Patterson function is twice the thickness of your object because your effect is going in both directions.
Mm-hmm.
And so if you're trying to fit electron diffraction patterns without image base, so you'd be fitting only diffraction intensity, you need to sample them and double that spacing. So that, and obviously your gap junction is, I don't know, 2 times 60 if that happens when you're at the spot angle 6. So that's about double. At the beginning, before you knew how it was going to fit, you must have had some idea about the thickness.
That's right. That's one thing that I should have mentioned. One of the way of determining what this number is using your biochemical information. How thick your crystal might be. You certainly don't want to go too far off. Okay. So now let's come back to look at all these parameters. So as I said, there are quite a few. So the first set of this defines the envelope for the inside in the real space. So this will be the model you'll be using for the fitting. Now the first thing is, of course, the Rmin and Rmax that defines the width of your envelope, and then you can apply a taper into it by defining these 2 numbers. It's going to apply half of Gaussian function according to the values that you put in there. So you're going to end up with a function. A function looks like this. One of the things is that once you start applying the tapering, it's no longer a square wave, so you cannot describe this in Fourier space directly as a sinc function. So one of the other things that you need to start specify then is how you're going to sample this envelope function, so that then you can do a discrete Fourier transform and put that into Fourier space as the curve. So those are the values that you use to describe the envelope function in a real space. There are a few of other things that's been used in the reciprocal space. One of them is that to perform the fitting, it needs to have some gas. So the way is have the gas is by creating some binning of your data in order to it make an assumption that everything in there is about the same value. Then it just averages out all your data points in there to give it an initial guess, and then it will do this square fitting using that to get the final result. So you need to specify that, and to generate the curve that we need to know. So there are two things here. Actually, it's actually separate. So there is 1/d, which is your envelope function. So you know where it dips to 0. The other one is that at the end, when you want to put this into making it into a 3D crystal, we may say, to have HKL value instead of a continuous HKZ star value. You need to sample your final curve with some value. That's where the imaginary the lattice parameter comes in. So you would define a lattice parameter, the lattice length in the third direction of your crystal. It has to be, as Richard said, that it needs to satisfy the requirement for the Patterson function, and of course it needs to be bigger than your envelope. And you can imagine that if you make it smaller than that, you basically even if you fit it like way, it's like cutting it off and trying to put another one of the same thing on the next unit cell. So that's not going to work either. So those are the important requirements. So you need to use those numbers so that you can sample it. There's another parameter in there. It's sometimes called confusion. That is called the del plot. It's really in there so that you can create a plot that you can read. So that it's the sample in your curve so that it plotted it out. Really, that's all it is doing. So that has nothing to do with the values over here or your envelope function. So that's all. There's always something that you need to consider. The weighing, the relative weighing of the amplitude turn and the phase turn. If you only have an image amplitude, you should weigh your phase higher. And if you have diffraction amplitude and the image phases, then you probably want to make it more or less even. Okay, so that's all about the lattice line fitting. So the result of what you will get, and what you should start to examine, is that what's the general fit of your lattice line to your data. And if it's not right, you should start to adjust the model. In other words, you should adjust your envelope function. And second is that do you have values that is jumping that's totally off from what the rest of the data scatter. You may need to refine your defocus field geometry. I'm going to have some. I have 2 examples to show you what that would do. And the third thing is that you may find that your lattice line, fits certain z values, and then it's got an empty area, and then they have more values after that. When that happens, that it means that your tail geometry distribution is not very even. So you should consider get more data. And the statistics that you get out of fun at the end of the program has two important numbers, and one is the overall weighted R factors, and that's based on the amplitude. And the other one, more importantly, is the overall weighted phase residual. So they are weighted by your IQ values. In other words, your signal-to-noise ratio. So if you get below 20, that's really good. It's unlikely that the first time you do this, it's going to be below 20, though. So what did you do to improve that? So in the first case, that you may have some of your defocus determined or astigmation determined slightly off, then what you will see is that most of the data which has corrected CDF determined, they are going to cluster at one point. The one that you have the wrong CDF estimate, most likely is good. Then if it's right at the edge, it's going to the wrong zone of the CDF. It's going to end up with 180 degree phase difference from the others. So in this case, I have one image that's it's off by 100 nanometer. So once I found that out, notice that this is the one that's closer to making a little small adjustment. I can make get it put to the other zone, the other side of the node of the CTF, and make that adjustment. Then it flip the phases, and it becomes in agreement with others. When I did that, just by doing on one images, that's my overall, my weighted phase residue dropped by 4. So you can see that it has a very big impact.
One out of many images that is connected for cost?
Probably like, if I remember right, about 40.
1 out of 40 images makes such a difference.
Yeah. Yeah. And in the other case, that so this is for tilt refinement. So maybe your tilt angle is a bit off, your tilt axis is off. Overall, it's reasonable, but there are a few out of all. This has to be small number, because when you are doing this fitting, it's sort of a self-consistent test. So this will only work if only a small number of your tail geometry is wrong. Same with your CTF. If most of them are wrong, then you are not going to get anywhere, because everybody will be scattered in different places. You will not know which one is right. So in this case, that there are a few of them, consistently, being off from the others. So by going back to Origo tails, turn on the tail geometry refinement option, I can get those tail geometry more correctly. So they are their tail angle were okay, but the tail axis were off, something like a 15 degree. So those are pretty big differences, really, once it's tilted. So when I correct those 3, then I can get my phase residual down by almost 10. So you can see that the differences it will make if you have all this error in your merging step and in your CDF refinement, CDF determination step. So you should use all this number to help you to improve your image processing. And then the last is for the tail geometry. And I created this plot when I was working on this set of data. The idea is that really don't have a good way of displaying our tail geometry distribution. So this is like a polar plot where the radius corresponds to your tilt angle, and the direction that's from the tilt from this axis will be your tilt axis now relative to your A star, for example. Now by plotting it like this, then you can see that now where all your tilt axes are for a given tilt angle or in certain range, and you can spot the region that's empty easier this way. The other thing that I put down here is this little scale bar here. Those two numbers are calculated according to the resolution that you want the data to go out to, as well as the thickness, your lattice parameter C. Basically, what it's telling you is that if I have two images that are separated by their tilt axes are separated by this much, and it's tilted to 40 degrees, then I have just enough part that's overlap at my highest resolution. Okay, so this means a 50% overlap. So you have two images that have a 50% overlap at the highest resolution in this range. Then that's a very good overlap between two images. And this number certainly is changing with the resolution that you are seeking, as well as the thickness of your sample. So this is another example of a virus capsid. It's in negative stain. It's very thin as well, just 110 used as the C value. So basically, any images will have some overlap in that way. So you don't require a very dense distribution in your tilt in your tilt in order to get a good enough oversampling to create a good fitting. Okay, so as I was supposed to mention something about the matrix. So the way I look at the matrix is that it's sort of the opposite of what we are trying to do. Well, we are using the information we get out from auric tail. So what we did in auric tail was that we move in a projection, move in a projection image, and try to put it to the same origin. And we were trying to refine the face origin, tail geometry, being tailed, and at that point we also have other information. At that point, we also try to standardize our A and the B values, and the B axis. MakeTrain does it the other way around. It takes your 3D map or 3D model, whatever you had at the time, do a back projection according to your crystal orientation. You know that from your image. And your image dimension, pixel size, as well as the CTF of that image. Try to recreate what this model, once it's reproject and put it into the microscope, what would it look like? So in those, you also have to use the information that you got out from auric tail, your face origin, tail geometry, your beam tail, if you have any, if you have it refined. And again, all these parameters that you already used in there, so that you will get back to the same coordinate system that you originally used in your image. So basically, it's the other way around. Now you end up being able to have a reference that's coming, reference inside your reference. You can use the Fourier unbending that's better than what a piece that's just being cut off from the image. So with that, that's all I have. And basically, what I'm trying to say here is that we are doing all these mergings and determining tail geometry, merging them together, doing lattice line fitting, generating density value. That's not the end of your project. What you're supposed to do after you've done this the first time, you should go back and see if you can make it better by using your information to see if you need to do more tilt refinement. Do you need to get your defocus better, or you can use your map to further increase your signal to noise ratio of the well-ordered information, which means ones at your diffraction spot. And if you need to acquire more images, if your TR geometry distribution is just really bad. Okay, so this is what I have. And any questions?
When you do the fitting or your observations on the latest line to a combination of sync functions,
right?
Can you assign a weighting to each observation depending on the quality of the image, of the original image?
You don't assign the quality factor for each image. The quality of the image will be expressed in terms of the IQ values of each of the spots that you get. So that's where you will get it from. Because this fitting is weighted by the signal to noise ratio that's derived from the IQ values. So basically that if your quality of the image is bad, you're not going to get a lot of spots at IQ1, for example, because they are not going to be very strong. So that's where that comes from. And as far as the resolution being, let's say one image is only go up to 10 angstrom and the other one has information all the way to 3 angstrom. Then the part that is being taken into account is normally during the merging, where you can specify what's your resolution limit that you're going to collect. You are going to merge your data into your final set. It treats them equally with weight. Each spot is weighted by its quality.
You have very nicely elaborated on the sort of very original approach to the fitting. And then you have alluded very quickly to make trend. Now, what is your personal experience? Which one of the two works better?
You need to use both. So it's really not a question of which one is better. The make trend is a way of giving you better references when you do the unbending. So that's basically helping you to go back to your image in order to get a better unbent image, improve your signal to noise ratio in order to get better lattice line fitting. So they are two different processes. Anything else? Okay.